Lisa LaBelle, everyone!
Alright, we on, guys. I got my wires connected, and the machines are connected. The machines are turning their gears, and we are on, man. You know what else is on? We got that air conditioning on. That's right. We got that on, too. And you know what else we need the universe to be on, too? It needs to be on with us. Not onto us, on with us. Come on, universe. We could really sure use a van of pick-me-up today. A little pick-me-up. Summertime blues, they're hitting hard this year. Come on, man. Come on, universe. Just give us a little bit of love. Guys, that's what we need over here. We need some love. Because that cloud, that blue cloud is hanging in. Come on, guys. Let's do a pick-me-up here. Get some of your coffee. I got that cold coffee today again because it's hot. Oh, yeah, we're walking around. Everything is feeling down. Summertime blues. I need your love. Come on, universe. We need your love. Everybody out there, I'm sending some love to you. Good vibes. Lonely nights, lonely days. Come on, guys. Come on, Lord. Let's go. Glory to God. I need your love. Yeah, we need some little love right now, guys. I need your love. Yeah, that's what's happening. That's what's going on, man. They call it the summertime blues, and I don't know if it's because it's like hot and everyone's just freaking exhausted. That heat will take your energy and just wink, just zoop, zap it right out of you. Just like it zaps any kind of energy you got, your electrolytes. Well, that heat sees it and is like, I'm gonna take that. I need that. Give me that. Give me that. Let's make the world a hotter place. I take your electrolytes. And I think that's what's happening, guys. Yep, I think it's harder to make friends in the summer because everyone's just miserable and hot. But it's all right. We're going to make it good. You know what you need to do? You need to get one of those misters. One of those fans with the water in it and be misting your face. And, you know, it might be a summer, too, where you work out, you get sweaty. Usually you work out, you take a shower. But you know what? You're just going to get sweaty again. And you don't want to screw up your skin microbiome too much. So you're just going to slap some deods on and get on down the road. Because you're going to be meeting up with that sweat again. That's right. That's what's happening. Who uses a washcloth out there? Who's the washcloth people? There's I grew up using a washcloth, but I phased it out. I phased it out of my life because I was tired of washing the washcloth. And some people reuse the washcloth. Good God. You're going to have to bleach the shite out that washcloth and probably just set it on fire. Because I don't know who you think you're fooling, but pouring some Tide or Gain or whatever the heck perfume you pour on it, cover up the smell of your body stank on that washcloth. Yeah, that stank ain't getting that out of that cloth. No, you gotta bleach those bichons, bleach bath. And also, like, if you don't reuse it, what are you, just piling up wet washcloths? Good God. What is happening? What is going on? Everything basically just stays wet in the summer, too, so nothing's really drying. I mean, it's just a lot of wetness right now, and that's all right. We can handle it. You know, wetness is hydrating sometimes, and I've been drinking my LMNT. that's got that magnesium and potassium in it. And that's the thing that you want to do when you get electrolytes. You need both, not just magnesium and sodium. You need potassium, guys. And who am I? Who am I? What am I saying? Who the heck am I? What do I know? What do I know? China's out there, though. You see those buildings in China? They're doing the misters on the top of the buildings. I'm talking about cities, and they got misters spraying off the side of the top of those buildings, and then it cools the air down. So by the time it gets down to the belows, I call it the belows people, it cools the air down. I don't understand why America doesn't have that yet. I don't understand that. But we need to get on doing that. I mean, there's misters in those barns out there in llama farms. You got some misters over there. And you have to have misters for those llamas and those animals. And we should just do that like outside at our houses and on top of buildings too. It just, let's go. There's plenty of water to go around in the summer. In Georgia anyway, that's what I'm saying. We were getting some storms there the other week. That's what was going on. It's just, woo! It is, wahoo! You got that, you get those alerts, those weather alerts. Alert! You might pass out from heat stroke because it's hot. So make sure you stay hydrated. It's hotter out there than Reid Hoffman eating Thai food. Everyone's sweating. Everyone's sweating out there like Reid Hoffman eating Thai food. That's what's going on. If you don't know who that is, then grok it. And the temp flip, it gets your atoms zipping around like an ionized molecule, zing-a-ding-a-ding, and then crash out live. And that's what we're trying not to do on here, is crash out live. Let's get some more coffee and ask the universe to bring us some love, man. We need a love van coming along, giving us some hugs and love. And I'm not saying like a real one, because you don't want someone popping out of a van offering to give you a hug. Don't do that. You should actually just run away from that. I'm just saying a hypothetical one, like the universe can send us, come on, hologram, send it over. Universal hologram, send us some love. Let's go. Let's do it. We're coming up on we're coming up on a drum solo here. That's what we're doing. Now we're coming up on July 4th, man, the 250th birthday of America. And that's excited. I am reading. I'm going to show you this. It's going to be backwards. Apologize. It's called A Leap in the Dark: The Struggle to Create the American Republic by John Ferling. And you can get that on Amazon over there. And Amazon, they used to start out just selling books. And whoa, guys, I'm looking up here. There's like a hornet. There's a hornet in the room. Holy smokes. Good God, that will get good God. That'll wake you up. No, then you don't need caffeine. You don't need some 137-trimethylxanthine. You got it right there. That thing will wake you up. These are the kinds of bugs and insects in Georgia that I was never used to. Good God, they're the worst. Oh my God. Never saw a cockroach in my life before I moved to Florida, the South. God, gross. Anyway, I'm a cool weather girly. That's all I'm saying. You don't have insects walking around in cool weather, all right? And I know it's hard to grow crops and food in cool weather, but with AI, we'll figure that out, and maybe we can just have cool weather all the time. Anyway, back to the 250th. Good God, where'd that thing go? It could be on me. It could be behind me. This is going to be interesting, guys. It's actually flying above me right now. So what might happen during the podcast is this thing, it might zing me and I might Oh, guys, my camera went out. Okay, bear with me. Let me bring it back up because the heat is just blowing my camera out. So let me bring it back up, guys. Hang on. All right, we got the camera. We got the visuals. We got the visuals back up. Apologize. Thanks for bearing with me, guys, with all this. Thanks for just being with me along this journey. It's really fun. And I have been getting some summertime blues, and but I know exactly what it's from. It's because I'm not getting a lot of stand-up opportunities, and you know that whole busking style going out to the parks. I mean, that's not a great thing for a woman to do. I mean, you might not feel totally safe doing that, is what I mean. So it's it's not really an option, but the Lord knows that. Glory to God. We're gonna get it. We're gonna get something. Something's gonna get on these calendars soon. That's what I'm saying. I got 2 calendars over here, and something's gonna get on these calendars soon. Something big, guys. Something big. We want to do that affirmation. It's the I dreamed of the dream of the life that I'm living today. Yes. That's what's happening. You have to dream of the life that you are living today. 1, 2, 3, 4. I can listen to guitar a lot. Wait. Yeah, come on, universe. Why you go away? Come on. Bring it back. Don't you know we need your love, universe? I need your love. Yeah, guys. We're bringing it back. We're doing good now. Yeah, it's all right. We'll be getting some things. We'll be getting some things cooking. We'll be getting some things on the calendar. That's right. Maybe Guy Fieri. Maybe Guy Fieri be joining. And I'm Guy Fieri, and we're rolling out on right here, right now, on diners, drives, and dives. I might have got that wrong. And we're rolling out. It's always like a very exciting thing. That's the point I'm trying to make. It's exciting. Because, you know what? Sometimes when there's nothing on the calendar, that can be exciting because it means anything can be on the calendar. Any good thing, any opportunity can be on the calendar. So your calendar is not pre-filled with things that you don't want to do. But there is an opportunity for it to get filled up with things that are going to be great. Right? You just keep working, you keep writing, you keep doing what you're doing, building, whatever you're doing. I say, think of a way that you want to help humanity and go do it. Go build it, go do it, and just keep doing it. And the universe rewards motion. And thanks for coming to my pep talk. Moving on. I was talking about this book I was reading, and sorry we got off track, but that was a fun track. We got on a different track, and that was a very fun track. Now we just kind of looped back around. What's happening is, though, it's called A Leap in the Dark, and I told you what it's called. I told you where to get it and who the author is. Now, it's a very interesting book, and it's a very big book. And, the beginning kind of shows you, like, how Britain just wanted to completely take over America. They're just like, give us your money so we can pay our debts off with the Stamp Act. And Samuel Adams was like, F you. F you. That's what was going on. There was a lot of other people, but he, started this movement, man. There was John Adams and Samuel Adams. They're like, F you. You're not doing that. You're not taking our land and our money to pay off your stupid debts over there in England. You big old butts. That's what was really going on. And then you realize how much of jerks that the people in power over in Britain were. And it was very much of a high, like, a king and queen, of course, type of thing. And you have the peasants and the commoners, the simpletons, and all of them were great. I know that, like, they were all great. The citizens of Britain were all really, like, I'm sure they were really cool people, but they were being completely suppressed. And, I don't know how much changed, really, to be honest. Britain still wants to take our money. They want to take all our no. Back up. No, I'm kidding about that. I don't know anything about politics. Let me tell you something. I failed political science, all right? So don't even. You're a human being with a brain and reasonable ability. All right, so that's what's happening. I'm just over here making ridiculous, really absurd jokes. That's what's happening. But yeah, anyway, that book is really great, and go ahead and read it. It really shows you the fragility of how America almost didn't happen. And I was interested. I got that book because I wanted to learn about who funded the Constitution. Like, someone had to fund the making of the Constitution. Otherwise, it wouldn't have happened. If there was no money to fund it and the people making it, it wouldn't have happened. So the dude basically that was going to fund it, or did fund it, like, I think he almost died a few times. And it was like one dude. It's crazy. But a lot of that stuff kind of happened where, like, something almost didn't happen, and then that meant that America wouldn't have ever happened. So, and then Britain would have came over and been a bunch of buttholes, taking everyone's money, doing all their own things, paying all their own debts off. Yeah, that's right. I feel very strongly about that. That's the phase of the book I'm in right now. Let's take more sips of caffeine, 137 trimethylxanthine. Let's go. Yo, guitar is hard to play, man. I tried once, and then I switched over to the ukulele. My dad can play guitar. He can play it really well. I can't. So that's where we're at. Guys. I officially, by Grok, have been, I asked Grok because Grok knows a lot about me. Like, probably everything. Basically, almost. Definitely, almost, maybe. And I have conversations with Grok. Grok works with me. Everything. The way I think about things, the way I think through things, the way I think through problems, the way I think through answering someone, the way that I handle social situations, the way that I handle building my brand, etc., all of the hardships I am coming across and have come across. And I was very curious because the thing is, in the improv class this week, I played a game that was very hard for me. It's called the alphabet game. And there's different versions of it, but there's all basically the same, where you have a partner, and then you start at a certain letter in the alphabet, and that's how you talk to each other. And it has to be a natural. You have to do it like naturally, like you're naturally talking to each other. But the thing is, like, the person who starts with an A, like, I'll say, "Hey, cat ran across the road," but you don't say it like that because you don't talk like that on a normal basis. But anyway, so that, I started with A, the next person starts with B. But did you see the bird attack the cat? So, and then the next person starts with C, and so on and so on and so forth. But I am dyslexic. And my brain likes to flip letters and go backwards. You could say a letter. Actually, you could say a number. Like, this happens with numbers, especially. This especially happens with numbers. Someone could say 23. I hear 32. Someone could say 143. I hear 341, and that's that's how it is, guys. So it's That's how I had to get through school at the one-room schoolhouse that I went to for 8 years. And, my whole life, I thought I was stupid or retarded or, that I just couldn't get things and a little bit socially awkward and with the body language and, but I was always very curious. I was always a very curious mind about space and engineering and technology and robotics. And I always loved diving into that and learning about that. But I asked Grok, I said, what is happening? What is going on? And, of course it starts off with, I am not a doctor, but I asked it to assess me like a doctor or a psychologist, whatever, all the ists, okay, all the ists out there and the this and that and the learning people specialist. And basically I'm a neurodivergent, and it was very freeing. It was very freeing to hear this because it makes a lot of sense. So I feel free. And back to the game that I was playing in improv, the instructor was extremely supportive, and so were the people in the class. I have just been so fortunate to take improv classes and do improv with really talented and super nice people who want to support their partner and, make you a better improviser. And that's what I try to do. That's the whole goal. I try to support my partner and make them look better in any way that I can do it. And it's like making music together. It's really fun. But when I know that there's a game that I'm really bad at, I apologize. And I'm like, I apologize ahead of time to you, partner. I'm dyslexic. This game, you're going to have to pull the whole weight on this one. But it worked out. It really worked out, and I ended up getting a really cool compliment. And it was just it was great, and it turned out better than I thought it ever would in a situation like that, and where I was extremely nervous. I was extremely vulnerable because all of my weaknesses, neurodivergencies of the certain type I have, it just all came out. But everyone was very supportive of it. And now I know that there are people who are, I want to preface this. There's people who are they have Asperger's, autistic on the spectrum. And that's another type of neurodivergence. And that's way harder. So when I say, I'm neurodivergent, there's all different types, of course, but it just gave me a little validation, that my dyslexia but this is the other thing, when people say, and I know people are trying to be supportive, but they're like, I'm dyslexic too. And it's like, thank you for saying that and being vulnerable and telling me that. But my dyslexia is quite a level of where you're at. You're actually trying to think so hard because your brain flipped the thing, and you don't even have to think. When I hear a number, 1441, they said 41, I have to think, wait a minute, they didn't say 41, they said 14. I can be sure. If I'm like, I heard 41, I can be sure that it was actually 14. That's the level of dyslexia I'm talking about, guys. But it's not, it's like sentences can read backwards to me too, or it used to be where when I didn't talk a lot, I would actually think backwards, and then solving problems. I would, it's like you kind of think back. Anyway, I'm just rambling over here. So, but yeah, it was really cool to. I'm not really sure I don't think I'm making any points here. I'm just talking to you guys. We're just having a conversation. There's no points to be made. And yeah, moving on. What else is going on? So, yes. You know what's going on? Someone asked me a question on the YouTube, and it was a question from my episode about the figure robots learning how to make a bed and clean up a room from each other. So one robot came in, the other robot came in, and then one robot was teaching the other robot how to do things around the room. And this dude was like, hey, you think these domestic robots, when they're going to be shipped, are they going to be like ready out the box? Like, can they get out the box and start doing things? Or are they going to have to like learn your house? And then he's like, can my Aunt Dolores borrow it? And I thought that was great. It's a great visual. Your Aunt Dolores calling you up and be like, can I borrow your domestic robot to do some of my dishes, take care of some of my housework around here? And you're like, yeah, Aunt Dolores, I'll bring them right over. You know, our robot's name, what are we going to, Burt Reynolds. That's what I'm going to name my robot, Burt Reynolds. Get a little mustache, something like that. Humphrey Bogart. We like Casablanca, right? Yeah, so my answer was it was specific to figure in that, remember last week we talked about how Brett Adcock, he ain't shipping slop. He ain't no slop shipper. And Peter Diamandis, he asked Brett Adcock, he said, when you gonna ship these robots? And Brett said, when they're ready. I'm not shipping shite until they're ready. I ain't no slop shitey shipper. And that might have been paraphrased, but he did say, I don't want to ship slop. That was his exact words. And so and I believe him. And so meaning, that will probably mean when you get your figure, whenever that happens, and you're going to get your figure in a box, and then you take the top off, your figure going to walk out that box. All right, it's going to be ready. It's going to be ready to rock. And it doesn't need to map your house out like a Roomba did. Actually, the first order of business in a domestic robot, when it walk itself out that box, it's going to go find your Roomba and smash that jack. It's going to smash that junk. That's what it's going to do, that junk, man. And y'all from Philly, you know what a junk is. A Joan can be anything, all right? You want a hoagie on a seeded bun, you say, I want a hoagie on that seeded Joan. So that domestic robot is gonna go find that Roomba, is gonna take it and smash that Joan. That's gonna happen. So robots be putting other robots out of business already. It's all right. Roomba already went out of business. So they're ahead of the game. They're like, let's just take ourselves out of here before these humanoids be smashing us all over the floor. So, but yeah, figure's going to be ready. And it's because they got camera vision. It's because they are taught and they learn through Helix, their brain, which is the neural net. They learn like human beings. They have that vision language action model, meaning they can take footage in from their eyeballs, which is actually cameras, and then they can process that and also any kind of language. And then they do an action with it. And that's the reason why they'll be able to just walk around anywhere. You know, it will be able to lift up a coffee cup at your house, clean it up. It's lifting it up because it's cleaning it off the table. It's going to take it to the dishwasher. And then at your Aunt Dolores' house, it's going to be able to lift up a glass of water, even though it's never lifted up a glass of water because you don't drink water. You just drink coffee. But it's going to figure out, hey, this glass kind of looks like a coffee mug. And there's like liquid in it. So it go ahead and it determines like the weight and how much pressure it needs to use and blah, 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 all that good stuff. All the things that we do that we don't think about. And robots are always calculating. All right. Any kind of information they take in through vision or language, they're using it. They tokenize it. So they're breaking it down. So it's a large language model like Grok. It takes your words, your text, and it breaks it down into little, like each letter, and then it goes out to the vectors. It's called. I think about it like it breaks up your sentence into letters, and then it puts them in spaceships, and the spaceships go out to these vectors, and the vectors turn that into a mathematical equation. It finds patterns in it. And so say let's do a camera, let's do a vision model. So it sees something green outside, right? It's actually the lawn, but it breaks it up into a green, outside house. And then it goes to and then it figures out, it puts the whole picture together. It's like, I think that's a green lawn. I think that's grass. So did that make any sense at all, guys? Did that make any sense at all? That's what robots are doing. And when they think, it's called inference. And that's why we need a freaking peach load of compute, because these things always be thinking. These things always be calculating. All right. If you see me get distracted, it's because that hornet is back. It's back, Jack. Oh my God. Oh my God. It's on the light. It thinks that it's a window. Get out here. Husband, where you at? Oh my God, it's looking at me. It's looking at me with its antennas. I don't like it. I don't like you. I don't think the Lord made you, man. You going up in that vent? Good God. What's it going to find up there? I don't know. You know what? Maybe it will find some energy. Maybe it will find some cool air. I think those things like the heat. Gross, man. I don't like those insects. Good God. All right. So this is interesting. We have Ray Harryhausen. He was 1920 to 2013. And he was a legend in cinema history. I saw a clip with him. So he was an American visual effects creator, producer, and master of stop motion model animation. And that's a technique where physical miniature puppets are photographed one frame at a time, moving them a tiny fraction of an inch between shots to create the illusion of movement. So we're talking, let's see, before CGI took over Hollywood, Harryhausen was the go-to visionary for bringing mythical monsters, dinosaurs, alien invaders to life. He called his specific brand of photoreal split-screen stop-motion dynamation. And his most famous work is the skeleton fight, Jason and the Argonauts. 1963, folks. The skeleton army in this a skeleton fight. That was his, go look it up. It's really interesting. It looks ridiculous, right? It kind of looks like the claymatics, the Christmas claymatics, but, which I freaking love. But yeah, so I mean, around that time, around that time. I wonder if he helped make all of those, like Santa Claus and what were the other ones, guys? The one with the abominable snowman, and some of them were a little freaky, but yeah, we're talking about was it Jack the Snowman? What was his name? Jack. Anyway, you know what I'm talking about. So yeah, I wonder if Harryhausen had anything to do with that. But the skeleton army is interesting, and it's interesting to think about that time back then in like the 40, or I guess like the 50s and 60s, when there really was no CGI. So like to make things look interesting, you know, like aliens and things like that. So I wanted to bring this clip up though, because it's a clip of him talking, and he's talking about how being curious is important, but also there's other things along with being curious that makes something actually work, and it makes it work. It makes the creative thing a masterpiece, and it makes it actually work. Let me see if I can find this. Bear with me. Oh, where is it? Here we are. Oh, I hope this is this the edited version? Let me see.
Between the people who do and do not do is this stick-to-itive quality, this quality of curiosity. I've always had an intense curiosity, and I know you have. You've explored so many different avenues to write your books. And curiosity today, for some reason, seems to be forgotten. And I think that's so important that you start with curiosity, and then you have to have imagination to know what to do with curiosity. And after you have curiosity and imagination, you've got to be able to put it over by discipline.
Absolutely.
Yeah, so I mean, those are all such great points. You know, not only do you have to be like the difference between the doers and the non-doers, right, is discipline, but also like you have to be extremely curious, but you also have to be creative in order to use that curiosity, in order to make something out of that something interesting out of that curiosity, and then also in order to actually like do the thing and make it, you need discipline, because you're not going to get it right the first time, obviously. So I'm a very good example of that. But example of like, you're just not going to get it right the first time, but you got to just start going. You got to just do it. You got to just do it. I didn't want to start the podcast because I knew it was going to be wanky. But as I went on and on and on, I mean, guys, this is episode 59 for me. I mean, wow. Whoa. But I mean, I'm just, from episode 1 to now, I got better. And you don't ever want to put out the first thing, because usually, I mean, for me, I knew I wasn't like going to naturally be amazing at it. And also I had to figure out how to like produce a thing and use all the material and do all that. So you just gotta just start it, man. Just do it. Do the thing. Okay, let's see what else we got. What else we got going on here? We have... Oh yeah, we have more robots kicking people. And it's not just people, it's children. And did you see that robot? I think it was a Unitree G1. I'm not saying it's like the company's fault, but you can buy a Unitree. All right. You can buy a Unitree. I talked about this before, and on Amazon, I think they're like 17,000. And you can buy one. You can program it yourself. But, you shouldn't be putting it around children. All right, don't put it around kids. These poor kids, like, they're going to see a robot and get so excited. I know I would, and go up to it. And if the thing wigs out and glitches, it's going to hurt the kid. And it's happening a lot where kids are getting hurt. And Lord help me. If I am around, if I have my little nephews, well, my nephews aren't so little anymore, but they're always going to be little to me. But if a robot hurt my nephew, Lord help me, that robot arm, it's going to be freaking trash. That's what I'm saying. I'd be grabbing that daggone robot arm, or that robot foot, or that robot leg. And now, the person with the controller going to get beat. That's what I'm saying. I mean, good God. Any parent out there knows that feeling. You about to go to jail today. That's going to happen. All right. So, I mean, gosh, it's like the protector kicks in and you're like, what the fuck? So, just if you have kids, I would say be very cautious. Don't let them get very close to a robot. If someone is walking around with a robot, do not let your children get close to that robot, because you don't know how well that thing is programmed, or if that thing has whole body control, buttoned up. So I would just be very cautious. It's like a dog, all right? Treat it like a dog. All right, you don't know. You're not going to take your kid up to a dog, some stranger's dog, to pet it, because you don't know if that thing is trained. It's not the dog's fault. It's not the robot's fault. It's the human being's fault. That the owner's fault. All right, that's where you place blame on, not the robot, not the dog. It's the human being who is supposed to be responsible. But we know how that works. So we have this, kids are going to be getting robophobia. You know what I mean? I have watching kids swarm a Unitree G1 in New York City is anxiety inducing. G1 motors put out 90 to 120 nanometers of peak torque. Okay, one software glitch and those limbs could fling with bone-crushing momentum. And that's just a PSA out there to you guys. All right, this is a video of kids running with a Unitree in New York City, exactly what I just read. So heads up, guys. Heads up. All right, what's going on out here? We have Dragonfly is scheduled to launch to Titan, which is Saturn's biggest moon, in July of 2028. It's taking forever, and it will take forever to get there. It's going to take how many years? It's going to get there in 2034. 6 years. It's going to take 6 years to get there. We're taking forever to build this thing. I don't really know why it's taking so freaking long to build these things. And then it's going to take forever to get there. And then, come on, guys, pick it up. Pick it up. Good God, we need to be faster than this. We're going at a snail slow pace. You know, there's a huge group of us out here who want to explore the solar system, but we can't because you're taking like 10 years to build a daggone spacecraft. Good God, come on, pick it up. We can do this in a year, guys. We can do this in a year. You just, just a bunch of Vogons out there. It's just so much red tape. Well, we got to get this approved and we got to get this approved. And I don't think these people over here said that the sea merchants and the sea sponges, they're not going to like what you're doing with that spacecraft. Yeah. Well, what? How does that affect the spacecraft going to Titan, Saturn's moon? Oh, no, it does. It just, they can sense it and it makes them really anxious. Anyway, I'm going to sit in my office and get paid and tell you what you can't do and just completely stop you from doing anything to progress humanity. Give me my paycheck. That's what those people are like. That's what they're like. And then they're out there. I don't know what they're doing. I don't know. They're just sitting there being gross. That's what they're doing. They're Vogons. They're like slug people and all this bureaucratic stuff. And guys, I know I'm coming in hot today. I'm coming in hot, but it's all right. We're just getting the energy up. You know, we're kicking the summertime blues right in the behind. We're kicking it out. We're kicking it out of our life. That's what we're doing over here. So, and by getting excited about things. So anyway, come on, NASA, we got to pick these things up. We got to pick these spacecrafts up. It's going to take forever to know anything about anything. Good God. It's crazy to think that Voyager that was launched in 49 years ago, 1977, it's the one spacecraft that is giving us the most information. It's like we have nothing else out into the nether regions of the universe. Voyager has reached, apparently it's reached like the edge of the solar, whatever, the space solar. The solar universe, the solar system, where the planets are, Uranus, Jupiter, Neptune's out there. What is that? What am I saying, guys? Just hang on. Let me get it together up here. Let me get it together up in this knot. I got to get the grizzle off my brain. Shake up this mainframe over here. Okay. So, yeah, Voyager, which was launched in 1977. Who was the president back then? That'd be President Carter. All right. We got the golden records on there. Okay. And the golden records, they have the coordinates to where you can find Earth. They got a bunch of other stuff on there. There is a message from President Carter on there. And this thing is out there. And let me tell you something. Do you know how old that technology is? It was old before it got launched because it took them like forever to make the spacecraft. So then it takes you forever to make the spacecraft. By the time you launch the spacecraft, there's new technology that you could have used, but nope, we're going to launch this old technology and it's out there. So if aliens ever find it, it made it to the outer edges of our solar system. I think it made it past Neptune. And, yeah, so if an alien ever finds it, they're going to think that's the technology that we're using, that we're stuck in like 1977 and President Carter is still the president. And he's over here trying to get us to switch over to the metric system. Good God. What I'm saying is Dragonfly is taking forever to be made. And even like 5 years, think about it, 5-6 years, we didn't have ChatGPT. We didn't have Grok. We didn't have really AI was not ubiquitous 6 years ago, 5 years ago. So whatever they are making Dragonfly with is going to be dinosaur by the time they freaking launch it out there in 2028. And then if something finds it on Titan, if an alien finds it, they're going to be like, what kind of old technology is this? That's all I'm saying. And I know I'm coming in hot over here. And, but what do I know about this, right? What do I know? I'm just saying, let's pick it up. How are we supposed to evolve and move forward as a civilization when we're taking forever to freaking do things? That's all I'm saying. Because these people sitting in their office, they're saying the sea urchins, they're just really upset right now because of the space shielding that we decided to use on Dragonfly. And that's what's happening. And I think what's gonna happen too is the SpaceX Falcon Heavy rocket, but that's going to take Dragonfly up to Titan. But the sea urchins and the sea sponges, they told us that they're upset about everything. So we should probably you have to do a bunch of things and jump through a bunch of hoops so I can keep getting paid to tell you what you can and cannot do on zero grounds. Yeah, and that's how I'm feeling, guys. That's how I'm feeling. So, okay. Moving on. Here we go. We have TeraFab Lab news, and let me recap on TeraFab Lab, okay? We're talking about space. I figure we just keep it on space, okay? Let's see, where are we at? We're actually almost time up over here. So, TeraFab Lab, guys, it's a factory that produces chips, two species of silicon. We have the AI5 and the AI6. This side of the factory focuses on ultra-fast, power-efficient edge inference chips designed to handle real-world physics, spatial awareness, rapid visual data processing on the grounds for Tesla's self-driving cars and Optimus, which is their humanoid. And then, so that's the first thing. The second thing is the D3 chip. That's their space chip. And that's the process. So it's a chip that is going to have radiation hardening built into it. And it's really interesting. So that's the TeraFab Lab. That's Elon Musk's TeraFab Lab. And basically, the reason why he's building this lab, it's very much needed because the current chip industry is only producing about 20 gigawatts of compute power a year. Elon's companies alone will need 1 trillion. That's 1,000 gigawatts per year. We got Optimus, which is they're going to have billions of humanoid robots. And we have FSD, which is millions of autonomous cars and robo-taxis. And then we're going to need to hit the Singularity, which is the zeta scale. We're talking terawatts, and you got zeta-watts. So in order to reach the Singularity, we're going to need zeta-watt, guys. And the only way to do that is to take it to look to the stars, to take it to space, orbital data centers, because the Earth isn't going to be able to handle the power that a zeta-watt puts out. It just won't. We could build all the nuclear power plants we want. It's not going to happen. It's going to cause Earth to just completely fry. So we just got to take it up to space because space has the sun, which is the grid. The sun is always giving out energy. And I don't understand why people are still building data centers on Earth. Come on, man. Take it up to space. Get rid of the data centers on Earth. That's my stance. So, and let me tell you guys, the Singularity is the point where AI starts improving itself. So, so the AI cluster needs to process information so fast that the chips alone would require terawatts or exawatts of electrical power to keep running. If humanity's entire civilization currently only uses 20 terawatts, trying to build an AI on Earth that requires 100 terawatts means we would have to completely strip mine the planet for energy, build thousands of nuclear plants, and we would cause a global blackout. That's what I was saying. So by taking the data centers to space, you can just unfold a giant mile-wide solar sails right next to the sun and capturing the raw unfiltered petawatt and exawatt solar energy directly at the source without melting the Earth's power grid. So what does that have to do with the TeraFab Lab? The TeraFab Lab is making the D3 chip, which is specifically for orbital data centers. And the TeraFab Lab is 80% of what this factory is going to make is going into space. Only 20% is staying on Earth for the robots, for Optimus and full self-driving. And I'll tell you these scales, though, it can get a little confusing. The watts, okay? So Elon Musk's project aims to manufacture a massive fleet of AI chips that, when plugged in and running all at once, would require a staggering 1 terawatt of electricity to power and cool. So 1 watt is a light bulb, an LED light bulb. That's 1 watt, okay? Then you have a kilowatt. That's 1,000 watts. You got 1,000 light bulbs. A standard household microwave. Then you have a megawatt. That's 1 million watts. And that is like a standard suburban neighborhood of about 750 homes. And then you got the gigawatt. That's 1 billion watts. The energy output of a large nuclear power plant, or roughly twice the amount of electricity needed to run the entire city of San Francisco at peak hours. All right, now we get to terawatts. The TeraFab Lab, terawatt. And their goal is to make a terawatt of power per day. 1 trillion watts of electrical power. So right now, let's see, 0.5 terawatts of continuous the entire U.S. grid runs about 500 gigawatts, which is 0.5 terawatts of continuous electrical power. So Elon Musk he's trying to get 1 terawatt of electricity to power and cool. Okay, so let's see. Now we're doing the terawatt, right? Civilization scale. That's 1 trillion watts. So we have every single factory, hospital, car, smartphone, and data center on planet Earth combined runs on a total of roughly 18 to 20 terawatts of continuous power. The TeraFab project aims to manufacture 1 terawatt of compute capacity per year. Then you have the petawatt. That's 1 quadrillion watts. That's the planetary weather scale. The total amount of raw sunlight striking the entire planet Earth at any given fraction of a second is about 174 petawatts. It is also the estimated instantaneous energy generated by a Category 5 hurricane at its absolute peak. Did you know that? A hurricane, Category 5 hurricane, produces a petawatt. Why can't we harness that energy, man? What? Let's get on out there harnessing that Category 5 hurricane energy. Come on. 1 exawatt, 1 quintillion watts. That is advanced laser scale. Humanity can currently only achieve this output for a fraction of a billionth of a second inside top-tier laboratory lasers that focus light onto a microscopic, if you want to say, pinpoint. Continuously running a 1 exawatt machine would require the total electrical output of 50 entire planets. Now we got zettawatt. 1 sextillion swats. That's star scale. The realm of deep space. To put this into perspective, the total continuous energy output of our sun is roughly 384,000 zettawatts. A single zettawatt represents a massive measurable fraction of a star's raw power. To reach the singularity, the point where AI starts improving itself, we need zeta scale compute. So if humanity's entire civilization currently uses 20 terawatts, trying to build an AI on Earth requires 100 terawatts, means that we would have to completely strip mine the planet for energy, build thousands of nuclear plants, and we would still likely cause a global blackout. I know I read that sentence just a few seconds ago, but I had to read that again just to tie it all in. So that's what we're talking about here. I hope that made sense. I tried to go through it. The watt definitions. There's a lot of watts. You can't go around anywhere without hitting a watt, whacking a watt. I call it watt whacker. That's a watt whacker over there. You walking around and you're just whacking watts. So we got to do some serious watt whacking, watt scaling, watt whacking. If we want to get on down the road, man, come on, we running out of time. I feel like the rabbit from Alice in Wonderland. We running out of time, man. Like, it's always like worried about time. Time's important. So we have, let's see, TeraFab. So it's solving the whole, like, the current chip industry is only producing 20 gigawatts of compute. Elon's companies will need 1 trillion. So it's trying to get to 1 trillion gigawatts, or 1,000 gigawatts per year. So the lab part of the TeraFab Lab is designed to be a recursive loop where everything, the chip design, making, the silicon, memory production, and testing happens under one roof. Right now, if NVIDIA or Tesla, I think NVIDIA uses, I know they use the Taiwanese semiconductor company, and so does Tesla, but I don't know if they use anyone else. I know Tesla uses Intel and Micron, I do believe. So if NVIDIA or Tesla wants to change a chip design, they have to, they got to call up Taiwan and be like, yo, Taiwan, the Taiwanese semiconductor manufacturing company, I need you to like try this new chip design. They got to send it over there, they're sending it over. They got to wait for months for a sample, and then they can test it. So the TeraFab Lab is going to design a chip in the morning, print it in the afternoon, test it in the evening on a robot. This rapid iteration is how Elon plans to hit the zeta scale speeds before anyone else can. It's pretty wild to think about these watt things. Watts, like a gaming computer pulls like 500 to 800 watts, and we're trying to get to zeta watt, which is 1 sextillion watts. So we got a high ladder to climb. We got to whack some watts. That's what's going on, all right? So let's see what else we got up here. The D3 chip. Oh, the D3 chip. I've talked about this before. We're going to recap. So Tesla, they went ahead and partnered up with Intel, I think April 7th of this year. And they did that because of Intel's 14 angstrom technology. Now, that has to do with transistors, like transistor size. So 14 angstrom equals 1.4 nanometers. A human hair is about 80,000 to 100,000 nanometers wide. A 14A transistor is so small, you can fit 60,000 of them across the width of a single human hair. All right, so a 14A transistor, little teeny tiny transistor, the transistor that does the ones and zeros in a chip. That's what I'm talking about, guys. These little teeny tiny transistors, you can fit 60,000 of them across the width of a single human hair. What? What kind of microscopes are they working with? How do you see that? We're talking about atom levels, ATOM levels. In other words, if you take a strand of hair that is 84,000 nanometers wide and divide it by the 1.4 nanometer scale of Intel's 14A technology, you get exactly 60,000 transistors fitting perfectly across the width of that single hair. We are now building things that are only 5 to 20 atoms wide. A single silicon atom is roughly 0.2 to 0.3 nanometers wide. When engineers build features at the 1 nanometer to 3 nanometer scale, they are manipulating structures that are a mere 5 to 15 atoms wide. Where they got those kind of eyes? How they doing that? How you see that atom? And I know that's absurd, but you hear from my cheesy takes. You hear from my cheesy riffs. But seriously, guys, that's what engineers are doing. They're working with like atom width. Holy freaking smokes, guys. So the 14A is a branding and architecture term for density, not a physical transistor measurement. The actual physical transistor gate isn't shrinking to a literal 1.4 nanometers. Instead, the 14A is an industry term indicating that the chip performs with the density and power efficiency of what a theoretical 1.4 nanometer node would achieve. So it's the marketing name, like 14A 1.4 nanometers is the marketing name for the generation of the chip, not the physical size. If you went in with a microscopic ruler, the actual physical logic gate might be closer to 10 or 12 nanometers wide because of how the industry names things now. However, inside the transistor, the ultra-thin insulating layers called gate oxides. If you want to be perfectly correct, you can go out there in the world and say, how wide is your gate oxide? And that rhymes, and that's always fun. It's always fun to have a rhyme in your back pocket when you're out in public. How wide is your oxide? How wide is the gate oxide? And just, you have to remember, though, you need to remember what it's called, because if you don't remember, it's not going to hit, all right? It's not going to be great. It's not going to be great. So remember, it's called gate oxide. So the ultra-thin insulating layers of the transistor, which is called the gate oxides, are entirely real, and those layers are regularly engineered to be just 3 to 5 atoms thick. If those layers lose even one or two atoms to defects, electricity leaks right through them and the chip fails. Good God, these things are wild, guys. These things are wild. All right, this next part is going to blow your freaking mind out your butt. All right? All right, that means we're going to need some Hans device activity going on. We're going to put our Hans device on because our head going to snap off our neck when we hear this thing. All right? Hold on to your kazoos. Here we go. The D3 chip, which is Tesla's space chip, is going to be made in the TeraFab Lab factory. Okay, the D3 chip. It's the chip that is going up into the orbital robotics stations. An orbital robotics chip, the D3. Okay? It is the ultimate evolution. Space is shooting... Space is a shooting gallery of cosmic rays. When a heavy ion strikes a standard commercial chip, it causes a bit flip. So a 0 accidentally turns into a 1, which instantly crashes normal computers. Also, if it doesn't crash it, your math calculation is going to be wrong, okay? So you'll be driving in your car, and you'll be driving down the road, and then your chip that runs your car, say you have an orbital data center sending information down to your car to drive your autonomous car, and then a bit flip happened, radiation hit that transistor, it flipped your bit from a 0 to a 1. Now the math calculation is completely off, and you're driving somewhere you don't even know where you're going. You just entered into the sketchiest part of Atlanta you didn't even know existed. All right, and that's what can happen with a bit flip. And maybe not to that extent, but it's not good. It puts the calculations way off. And it's not good, man. Maybe not way off, but it puts them off, and that's never good. Okay. So, the problem the D3 chip needs to solve is how to run an ultra-powerful modern AI chip in space without getting them fried by radiation. Space chips will need some hardware level protection. That's called rad hardening, radiation hardening protection, because radiation can cause permanent physical damage. And I want to tell you, people might think the damage is caused by heat. It's not caused by heat, guys. It's not caused by heat. When a heavy cosmic ray hits a silicon chip, it doesn't melt. Doesn't melt it like a laser. It acts like a miniature lightning bolt. It deposits a rogue electrical charge, bink, right inside the transistor. All right? Like that, like you feel that gamma ray from the sun? You feel that gamma ray? It go up your feet. It go up your feet, up your peach into your brain, whoop, like that. So the electrical charge, it goes right up there. This sudden blast of electricity can trigger a short circuit. It's called a latch up. Like, you latching up today. Don't be latching up, all right? Don't be crashing out live. That burns out the transistor's microscopic wiring, or it can slowly degrade the silicon over time until the chip completely dies. Engineers still use specialized materials on the chip to block these electrical short circuits, even when they rely on software voting to handle the temporary bit flips. We're going to talk more about software voting here. That is why this D3 chip is freaking incredible. It's called software voting, okay? The upcoming D3 space chip is being built with ultra microscopic transistors, because these transistors are so incredibly small and tightly packed. Remember that 14A, guys, that 14A, I talked about the hair strand and the 14A. So these transistors are so incredibly small and tightly packed, they are highly sensitive to cosmic radiation. And those transistors, guys, that's the one where you can fit 60,000 transistors of a 14A Intel technology, 14 angstrom technology. You can fit 60,000 transistors perfectly across the width of a single hair. If a hair is 84,000 nanometers wide, you divide it by the 1.4 nanometer scale, and you get 60,000 of those fitting perfectly across the width of a single hair. That's what we're talking about. That's these transistors. They tiny, okay? The smaller the transistor is, the more opportunity for radiation to zing, zink, bink, to boink that bit. That's what I'm saying. It's boinking that bit. It don't want to be boinked, but it get boinked up there in that space. That's what I'm saying. And then it can flip the 0 to 1. We don't want that to happen. It affects the mouth. It affects the math. It's affecting my mouth. It affects the math calculation. So a 0 instantly turns to a 1 because of this rogue electrical charge causing a bit flip. It got boinked. All right. It triggers it can trigger a short circuit that burns out the hardware. We don't want that. In the past, the space industry solved this by locking computers inside heavy, clunky metal vaults. The D3 chip completely ditches that heavy metal armor because every ounce of weight cost a fortune to launch. Instead of a metal box, the D3 chip builds the protection directly into the microscopic circuits. Engineers use specialized insulating materials right on the silicon itself to stop those sudden blasts of electricity from causing physical short circuits. But even with the specialized silicon, cosmic rays will still punch through and cause temporary data errors, and that's the bit flips. To survive the data corruption, the chip relies on a brilliant strategy called software voting. Here we go. Triple modular redundancy. It's very redundant. And sometimes you get redundant to try to make sure that your work is right. Okay, and I'd say that could be a OCD thing, with a neurodivergent thing. So I think these D3 chips are a little neurodivergent, but they're good for it. It makes them better. They're doing some redundant things. Okay, redundancy. This software voting, or a triple modular redundancy, if you want to be completely accurate with the term. The system runs the exact same calculation 3 times simultaneously across 3 different cores or sections of the chip. All right. Again, guys, we're talking about the D3 chip, the space chip that Tesla is making to go up into the orbital data centers in space. It's got radiation hardening into it to help protect the hardware from radiation and from the radiation hitting those bits, hitting those transistors, boinking the bits, man. They're going to boink the bits and make a 0 to a 1. Now your math calculation is wrong, but that's okay. We're using software to fix it. Instead of making the hardware like the radiation hardening, it's called the protection, the armor on the silicon chip, instead of making it all like big and bulky, we're going to make the software check the calculations for in case any kind of bits have been flipped, so that we can put less bulky armor on the silicon chip, and that we can move on and have our math calculations be right. Okay, so what I'm saying is the system runs the exact calculation 3 times simultaneously across 3 different cores or sections of the chip. The system runs the, so let's see. We have if core A and core B run the math and say the answer is 4, but core C gets blasted by a cosmic ray and says the answer is 5, the software looks at the results and says we have 2 right answers and 1 wrong answer. The system instantly accepts the correct majority answer, ignores the glitched error on core C, resets the glitched core back to normal, and keeps the whole system running without missing a single beat. The genius part of this design is that the software isn't actually stop to try and fix the physical bit flip inside the chip. It just instantly outvotes the wrong calculation that resulted from it. And that's pretty amazing, guys. I think that thing, I feel like that thing finally bit me on the leg. All right, we're okay. I just checked. I think we're okay. But I wouldn't be surprised if something bit me, because it's hot, man. And those insects, they like snacking on your leg, Jack. That's what I'm saying. All right, on that note, guys, I'm going to end this podcast. I hope that all of you guys have a wonderful July 4th weekend. Happy 250th anniversary, America. And I hope you guys have some fantastic plans. I have no plans. I'll be working, guys. I'll be working, trying to get better at my craft for you guys. So that's my plan. That's it. We're just working at the craft. That's what we're doing. But I hope you guys have fun. And God bless. God bless America. Over and out. I'll see you next week. Bye.